So in this video I want to talk about section 11.8. Here we're going to talk about what are called power series. And a power series is a new way to define a function, and we're defining a function using series. And so the general form here is that you're going to have some sequence c sub n times x minus a to the n as n goes from 0 to infinity. And in this section and in the following sections, just in case it comes up, by convention we let 0 to the 0 equal 1. Even though technically 0 to the 0 is indeterminate, 0 to the 0 we're letting it just be 1 in this case, because that's what it should be when we're talking about power series. Maybe there's other situations where it should be something else, but for now 0 to the 0 is 1. That comes up, for example, because if you were to plug in the value x equals a, you would have 0 to the n, where n starts at 0 and goes to infinity, and you have a 0 to the 0 term. So it's just kind of natural here to just let 0 to the 0 be 1. Now, this function f, if you write it out, if you think about what the first few terms are, you have c0 times x minus a to the 0, which is 1, plus c1 times x minus a to the first, plus c2 times x minus a squared. You'd have a c3 times x minus a cubed, and so on. And so here a is just some real number. It could be 5 or pi or negative 2. And it's called the center of the power series. Okay, so a is called the center of the power series. And notice that I don't care what the sequence is. This function is always defined at least a single point, namely at a. And so if you plug in a here, what would happen is you would pick up this first term no matter what, and then when you plug in a, all these other terms vanish. They all go to 0. And so this is definitely going to converge at x equals a. So there's always at least one value where these make sense, where they converge. And again, that value is called the center of the power series. Now, we've seen some examples. In fact, we know from what we've learned about geometric series that if I were to take a function f and define it as the sum of x to the n as n goes from 0 to infinity, this converges. Actually, not only do we know that it converges, I might as well say this converges to 1 over 1 minus x if and only if the absolute value of x is less than 1. Okay, and so that's something that we already know about all geometric series. Now, we can use that, for example, by looking if we have, say, if we had x plus 2 to the n all over 3 to the n. And we wanted to figure out, does this sequence converge for some particular values, and if so, what values? Well, this is just a geometric series. You could actually rewrite this as x plus 2 all over 3 to the n. And so we know that this is going to converge. In fact, we know what it converges to. I care less about what it converges to in this case, but we do know that it converges to that. If and only if the thing that we're adding, so in this case, the absolute value of x plus 2 over 3, is less than 1. And to say that that's less than 1 is to say that the absolute value of x plus 2 is strictly less than 3, or that's equivalent to saying that x plus 2 is between negative 3 and 3, or finally, that's equivalent to saying that x is between negative 5 and 1. So these are exactly the x values where this function that we defined here, these are the x values where that function converges, and we know one more thing. We know that it converges to this quantity here, 1 over 1 minus the quantity x plus 2 over 3, okay, which we could simplify if we want, but I don't care for now. Okay, so that's one thing that we can do, and we can use everything that we know about geometric series to figure out what are the values of x where the series converges. Now, the other thing that we can do with these series is that if we were to look at a series such as, let's look at f of x is, say, negative 1 to the n times x minus 2 to the n all over n squared times 4 to the n. And here n has got to go from 1 to infinity. I care less about what it converges to. This is not a pure geometric series anymore because of this n squared in the denominator. And that n squared, by the way, is also why the sum has to start at 1 and not 0. But what we can do in this case, when we want to find out what are the x values where this converges, I should actually write that. Find all the x values. That's what we did in the previous case. That's what I want to do here. Find all the x values so that f of x converges. What we can do is we can apply the ratio test or the root test, whichever is better for the given function. In this case, let's do the root test. So I'm going to let L be the limit as n goes to infinity of the nth root of the absolute value of our sequence that we're summing. So negative 1 to the n, x minus 2 to the n, all over 4 to the n, and I forgot the n squared, so let's put that in now. And when I take the absolute values, what ends up happening is that the negative 1 to the n becomes 1 to the n, and so that's just a 1. The x minus 2 to the n becomes, we still need the absolute values there, but we can write that as the absolute value of x minus 2 all to the n. And then we're left with n squared over 4 to the n. And so when we take the nth root, this is going to turn into the limit as n goes to infinity of the absolute value of x minus 2 all over n to the 2 over n times 4. And as n goes to infinity, n to the 2 over n, as we well know, goes to 1. And so this is going to end up being the absolute value of x minus 2 all over 4. And so now we can apply the root test. And we know that this is going to converge if this quantity is less than 1. Okay, so this function that we were defining up here, so this function converges for those x values, if x minus 2 in absolute value is less than 4. And let's actually talk about what are those values. So here, if we have x minus 2 in absolute value over 4 is less than 1, that means that x minus 2 in absolute value is less than 4. So this means the absolute value of x minus 2 is less than 4. That's equivalent to saying that x minus 2 is between negative 4 and 4, and that's equivalent to saying that x is between negative 2 and 6. Now, what's different here, and what was really nice last time, is that we knew everything about geometric series. We knew that it converged for geometric series, you know that it converges if the absolute value of x is less than 1, and it diverges otherwise. So when I say if and only if, I'm saying if x is in this interval, if x satisfies this inequality, the series converges. If it doesn't satisfy this inequality, the series diverges. Here, when we use the root test, we actually have just one more little ounce of work left to do. We know that this series is going to converge if this value is less than 1. We know that the series, so let me just write this down. So the series that we're looking at was negative 1 to the n, x minus 2 to the n, over n squared times 4 to the n, as n goes from 1 to infinity. We know that this converges if x is between negative 2 and 6. We know that this diverges if x is less than negative 2 or greater than 6, and that's just by the root test. We know that if this value is strictly greater than 1, then the series diverges by the root test. But what's left is what happens when this quantity, what happens when that equals 1. And so we still have two other values to check, namely the endpoints of our interval from negative 2 to 6. And so let's just do that by hand. By hand, I mean without the use of any tests. We just are going to evaluate f of negative 2. That's going to be, we're going to have negative 1 to the n times negative 2 minus 2 is negative 4 to the n, all over n squared times 4 to the n, because n goes from 1 to infinity. And so that's going to end up being negative 1 to the n times negative 4 to the n is going to be negative 1 times negative 4, or positive 4 to the n. And that's going to actually cancel with that 4 to the n in the denominator. And so this is going to end up giving us 1 over n squared from 1 to infinity, which converges. It's a p series with p equals 2. Okay, so that converges. Likewise, we have to check what happens at 6. This is going to end up being negative 1 to the n times, let's see, if we plug in 6 for x, we're going to end up with 6 minus 2 is 4 to the n. And that's all over n squared times 4 to the n, as n goes from 1 to infinity. The 4 to the n's are going to cancel. We end up with the alternating p series with p equals 2. Okay, this again converges. Actually, it converges absolutely, but all we care about is that it converges. Okay, and so essentially what we just proved is that we're done with this problem. This series that we were looking at, this negative 1 to the n, x minus 2 to the n, over n squared times 4 to the n, as n goes from 1 to infinity, converges if x is between negative 2 and 6, including both endpoints, which is the work that we just did previously. So that's what we just did here. So it converges there, and it diverges otherwise. So it diverges if x is less than or equal to, strictly less than negative 2 or strictly greater than 6. Okay, so there's a little bit more work that we had to do there. Generally, when you use the root or the ratio test, you're going to have to check the endpoints manually, just by hand. Okay, so you'll have to do that by hand sometimes. Okay, before, when we had the geometric series, we know everything about that. We didn't have to check the endpoints. We already knew that those diverged for geometric series. But here the endpoints of our interval turned out to converge, and so we include those in the set of x values where the series converges. Now, what turns out to be the case, and this is true of all series, of all power series, I should say, but what turns out to be the case is that the set of all x values where the series converges is an interval. Okay, and so the set of all x values where a series converge is always an interval. The interval has some length. Okay, so half the length of this interval, so half the length of the interval is called the radius of convergence. And notice that the interval is centered. I forgot to say, and I should go back and add this here. The interval where all the x values converge is called the interval of convergence. Okay, the interval of convergence is centered at A. Okay, and so what I mean by that is that if you were to talk about the power series c sub n times x minus a to the n as n goes from 0 to infinity, or from 1 to infinity, or whatever, this is going to converge for a particular set of x values. Those x values are called the interval of convergence, because it turns out that that is always going to be an interval, and the interval is going to be centered at A. So, for example, going back up one more time to this example that we just did here, this interval converged from negative 2 to 6. So we go from negative 2 to 6, and lo and behold, halfway between negative 2 and 6 is the center of our interval, which is 2, and that's because we had this x minus 2 to the n, and so 2 was the center of the power series. And so here, this converged for these yellow values from negative 2 to 6, including the endpoints. Okay? Whether we include the endpoints or not, this interval is still going to be centered at 2. Okay. So that's the interval of convergence. That's the radius of convergence. We denote the radius of convergence by using a capital R. Okay. Sometimes the interval of convergence is infinite, in which case we let the radius of convergence be infinite. So this would be something like, I'm just going to have some simple examples here, but something like x to the n over n to the n, as n goes from 0 to not 0, as n goes from, say, 1 to infinity. Okay, so here, if you were to apply the root test, what you would do is you would look at the limit L, which is going to be the limit as n goes to infinity of, let's see, x to the n over n to the n. So we're going to take the nth root of the absolute value of x to the n over n to the n. And this is going to be the limit as n goes to infinity of, let's see, the nth root, we're going to bring the absolute value inside. So this is the nth root of the absolute value of x over n to the n, which is really just the limit as n goes to infinity of the absolute value of x over n. And no matter what x is, that limit's going to be 0. And so that means that this is going to converge for all x values. Every x value is going to satisfy this inequality. Okay, so this limit is going to be 0 for all x values. And so therefore, the interval of convergence, so the interval of convergence is going to be all real numbers. The radius of convergence is infinity, and we still think of 0 as the center of the interval of convergence, or the center of the power series, because this is x minus 0 to the n. Right? When you have x to the n, it's just 0 as the center. Okay, so that's possible. It's also possible that if r is 0. And so, for example, that would happen when you have something like 2 to the, let's do this carefully here. Let's say n factorial times x minus 4 to the n. And it turns out by the, here, since we have a factorial, we better use the ratio test and not the root test. But it turns out since we have this n factorial times x minus 4 to the n, this converges, I'll let you do the details here, but this converges, well, I don't know why I'm not doing the details. Let's just do it together. L is going to be the limit as n goes to infinity. We're going to look at the n plus first term over the nth term. Okay, and then as usual, n plus 1 factorial over n factorial is n plus 1. The absolute values, we can, we don't need them for the factorials, but the absolute value of x minus 4 we'll need. So this is going to end up being n plus 1 times the absolute value of x minus 4. And it turns out that this limit is going to be, it's going to end up being 0 if x is equal to 4, and it'll be infinite otherwise. And therefore, x equals 4 is going to be a value where this series converges, but it's going to diverge otherwise. Okay, so this converges only for x equals 4. Notice how I said that the interval of convergence is always an interval. Well, our interval of convergence, I'm cheating here slightly, but not really. That's the interval from 4 to 4. You can still think of it as the interval. 4 is the midpoint of the interval, therefore it's the center of the power series, or the center of the interval of convergence, and everything there is still totally fine. Okay, and so what we're going to do for now in 11.8 is just talk about these types of power series, figure out where are the series going to converge and whatnot. There's one last thing I should mention about the radius of convergence. And here the radius of convergence, if you kind of think carefully about what we're doing with the ratio test and the root test, you can use something like that to determine what the radius of convergence is going to be. And so if you have the function c sub n, x minus a to the n, here it turns out that the radius of convergence is going to be given by basically the root test just applied to c sub n, where we're going to take 1 over it. So it's the reciprocal of the limit that we get from the root test, so like 1 over L, where L is the limit as n goes to infinity of the nth root of the absolute value of c sub n, or equivalently, L is the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. Okay, so this is the kind of thing that you can do to find the radius of convergence. And this, we'll do this in a following video here. But we can use this as well to find the interval of convergence. So if we were to do this to that function -1 to the n, x minus 2 to the n, all over n squared 4 to the n, you would see that you would have your r would be 4, and then therefore this would be some interval from 2 plus or minus 4. So that would be kind of the interval that you're looking at. So 2 plus 4 would be 6, and 2 minus 4 would be -2. And then you'd still have to figure out, do you include the endpoints, do you not include the endpoints, and so on. Okay, so you can actually do finding the interval of convergence that way as well. We'll do some examples in class and in the next video.